Have you ever thought about the universe as, well, a book? A book written in a very specific, very powerful language. Well, today, we're going to learn how to read it.
I mean, that's a huge question, right? How does physics actually write the rules for everything? You'd think it's all about these super complicated, impossible to memorize equations. But what if I told you the real secret is just learning a language? And get this, it's surprisingly simple once you see the pattern.
Yeah, so let's just push aside all those scary-looking equations for a few minutes. We're not doing a math lecture. Instead, we're going to crack the code. We're going to find the alphabet, build some words, and even learn the grammar that physicists use to tell the story of the entire cosmos.
Okay, so where do you start with any language? You start with the alphabet, right? The absolute basics, the core building blocks. And physics is no different. Its alphabet is what we call the foundational units of measurement. So, take a guess. How many letters do you think we need for this cosmic alphabet? 100? Maybe 1,000? Nope. And this is the part that just blows my mind every time. There are only 7. Just 7. And here they are, the magnificent 7. You've got length, you know, how far something is, mass, how much stuff is in it, and of course, time. Then we get a little more specific with electric current, temperature, the amount of a substance, and luminous intensity, basically how bright something is. That's it. These are the fundamental, can't be broken down any further letters. Everything else in physics is just a combination of these 7. It's wild. All right, so we've got our alphabet. What's next? Well, you put the letters together to make words. And this is where physics starts to describe the stuff we actually see and interact with every single day. And the way we do this is, well, it's kind of like following a recipe. You just mix and match these fundamental units to cook up more complex ideas. These are our physical words. Let's walk through a couple of easy ones. First up, velocity. Super common word, right? It just means how fast is something going. All we do is take one of our letters, length, and divide it by another one, time. Think meters per second. That's it. We just made our first word. Pretty simple. Okay, let's level up. What about acceleration? That's just the change in velocity. So we take the word we just made, velocity, and we ask how it's changing over time. That just means we divide by time one more time. So you get length divided by time squared. Now for a big one, a really powerful word, force. You've probably heard of F equals ma, right? Newton's big idea. Well, it's just an object's mass, one of our original letters, times its acceleration, the word we literally just defined. See how we're building here? It's like stacking Legos.
And this is the real magic. This idea of force, which sounds so complex, is really just a sentence made from our original alphabet, mass times length divided by time squared. If you take away one thing, let it be this. No matter how complicated something in physics sounds, you can always trace it back to those original 7 building blocks.
But you know, sometimes just knowing how much of something isn't the full story. For some of our physics words, we also need to know which way. Direction matters a lot.
So there are some things that are perfectly described by just a number, just a magnitude. We call these scalars. Think about the temperature in your room. It's 72 degrees. That's it. Or the mass of a bowling ball. It's just a number. No direction needed. And this difference between scalars and vectors is absolutely critical. A scalar is just the number, but a vector has the number and a direction. It's the whole package. Like if you're pushing a car, it really matters how hard you push, that's the magnitude, but it also really matters which way you're pushing it. That combination makes force a vector. Same with velocity. 20 miles per hour is a speed, a scalar, but 20 miles per hour north? Now that's a velocity. That's a vector. Okay, so quick recap. We've got words, and some of those words have a direction. But a direction like north or up is kind of useless unless you have a map to put it on, right? We need a frame of reference. In physics, these maps are called coordinate systems. You can think of them as the stage where all the physics happens. And the cool thing is, physicists are smart about it. They don't just use one type of map. They pick the best map for whatever problem they're trying to solve. The one you probably know from math class is the Cartesian system. The easiest way to picture it is a city grid. You go a certain distance down X Street, a certain distance over on Y Avenue, and maybe up or down on Z Boulevard to find your exact spot. It's straightforward, super useful for a lot of things. But what if you're working with something round, like a pipe, or even just a soda can?
That city grid suddenly feels really clunky and awkward. So instead, we can use a cylindrical system. All you need is how far out from the center you are, what angle you've rotated around, and how high up you are. It just fits the shape of the problem so much better.
And then, of course, for something like a planet or a star, a sphere, we've got the spherical system. This one's actually really intuitive. It's basically just latitude and longitude, like on a globe, plus a third number, your distance from the very center. So you see, each system is just a different kind of map for a different kind of terrain.
All right, we've got our letters, we've built some words, and we have maps to navigate. There's just one last piece to this puzzle, the grammar. These are the advanced rules that let physicists write really complex, really powerful sentences about how the universe actually works.
We call these grammar tools vector operators. And look, don't get hung up on the name or the math behind them. That's not the point right now. The important thing is to get a feel for what these tools do, the kinds of stories they let us tell. So the three big ones are called gradient, divergence, and curl. A gradient basically asks, which way is uphill? If you have a map of temperatures, the gradient points in the direction where it gets hotter faster. Divergence measures how much something is spreading out from a point, kind of like water spraying from a sprinkler head. And curl is exactly what it sounds like. It measures rotation, or spin. Think of water swirling down a drain.
And it's with this grammar, these advanced tools, that we can finally describe all the invisible forces that are running the show: the pull of gravity, the flow of an electric current, the weird push and pull of magnetic fields. These operators are the language we use to write the rules for all of it.
So, let's pull it all together. We started with an alphabet of just 7 units. We used those to build words that describe things like velocity and force. And we finished with a sophisticated grammar that lets us talk about invisible fields. We've basically learned the language physics uses to read the universe. And now that we're starting to get fluent, it makes you wonder, doesn't it? What new stories are we going to write?